Okay, welcome to the 10th chapter. This is the last chapter of Integrated Math 3. Um, we are going to be going into statistics, and statistics is in probably the most applied part of math that you can get into. And in today's world, everything experiments are being done constantly, so the statistics is a really important part of it. However, you're pretty much not going to need to use anything that's further than this in statistics. And plus, I know most of the people watching this will go to calculus anyways. So, however, if you do want to go to statistics, this is a very good introduction to the kind of higher level statistics that you're going to be seeing in college and beyond and in your job. So today is we're going to be looking at standard deviation and z-score. And standard deviation, also known as standard error, can also be known as standard error. And we also be talking about what a bell curve is. A bell curve is what they call a normal distribution. And the reason why it's called a normal distribution is because um, people aren't much worse. The majority of people aren't much worse than the bell curve, the mean of the bell curve, the center of the bell curve. Neither are they much better than the center of the bell curve. So basically, the median is the mean. The median is the mean. The half half the people are worse than the bell curve, and half the people are better than the bell curve, or half the results are less than the mean, and half the results are better than the mean, right? Or more than the mean. So the general equation of this bell curve, for the standard equation for the 100%, if the bell curve had the area of 1, is bell curve is 1 over 2 pi, 1 over the square root of 2 pi e to the minus x squared. And obviously, you don't want to be memorizing any of that formula. We're not going to memorize any of these formulas. This is just an interesting thing. Once you go to, I don't know, statistics-based calculus, you will see this formula, right? Calculus-based statistics, not statistics-based calculus. And we'll also be talking about standard deviation. Standard deviation is a measure of change, right? Change. So change means how much they differ by. Change means how much the data points are going or away from each other. So standard deviation is a measure of change, means how much the data points are separated away from each other. And this is the bell curve, and the standard deviation kind of marks the sections of the bell curve that constitute uh, kind of how rare the result is. So in this, for example, in this we will have this is 1 standard deviation, 2, 3, right, and then the mean is by this symbol right here. It's mu, and sigma is the standard deviation. So this is mu plus 1 sigma, which means the mean plus 1 standard deviation. And if you're beyond that, you're 1 standard deviation above the mean at least. This is 2 standard deviations above the mean. This is a standard deviation below the mean. And this is 2 standard deviations below the mean. So that's kind of like the idea that we're trying to get to is standard deviations separates the kind of the cohorts, the sections of how good you are compared to how rare is your results compared to the mean. So we're going to try to find the standard deviation of some, and there's this complicated formula, but I'm going to tell you what the formula actually means. It means you square everything. Okay, it means okay. I'm gonna illustrate through this example. So we have find the standard deviation of 5, 8, 2, 6, 4, and we have a mean, and the mean is well, we have to find the mean, and we have to square all of them, right? And I'm gonna find the mean right now. So 2 plus 4 plus 5 plus 6 plus 8 over 5. This is the mean, right? The mean, and the mean is 25 over 5, right? We always use Greek letters to signify. So the mean is 5, right? And then what's this xn minus mu squared? What does that mean? Well, it just means you take every single data point right here, and then you subtract it by 5. So 2 minus 5, and then there's a sum. There's a sigma right here, and the sigma means you have to add all of them together, and then divide it by the mean again, divided by the number of data points again. So 2 minus 5 squared plus 4 minus 5 squared plus 5 minus 5 squared, so plus 0, plus 6 minus 5 squared plus 8 minus 5 squared, right? And then you divide all this by 5. Since there's 5 data points, you take the square root of it, and that's sigma right there. So sigma is, I'm just going to calculate it real quick. So this square root, this is 2 minus 5 squared, which is 3. So that's 9 plus, is this still on the screen? Yeah, hopefully it is. So 9 plus 1 plus 1 plus 9, since 4 minus 5, 6 minus 5, over 5 square root. And that would be equal to 20 over 5 square root. So it would just be equal to square root 4, which is equal to 2. So the standard deviation of this set of data points is 2. So we could draw a bell curve of where we have this, and then the mean is 5, and then we have one standard deviation is 5 plus 2, and then the other is 5 minus 2, which is 3, and then we could place all of our data points. Our 2 is one standard deviation below the mean, 1 or more, and it has a z-score. We'll be talking about what z-score is later, but it has a z-score of minus 1.5, and then the 8 is more than one standard deviation above the mean, has a z-score of plus 1.5. So that's like a sneak peek of what the z-score is. So these are the probability sections of the bell curve right here. The middle, smack right down in the middle, is 50%. So you are 50%. You are in the median. You are in a median if you have results that are right smack in the middle. If you pick a number out of the data set that's right smack in the middle, it's the median. But if you pick a number that's 80% above the data set, then you could see that it'll land around here, which is just nearly one standard deviation above the mean. It's about 0.9, 0.8, right? And the 0.9, 0.8 score that I'm talking about, that's the z-score. So the probability of being one standard deviation above the rest, right? The probability of being one standard deviation above, this is a bad question, because it's the answer is 0, but above the rest or more, I should say. So what's the probability of being one standard deviation above the rest or more? Well, let's see. We'll have this. We know that the center is 50%. So being one standard deviation above the rest or more means you're here or better. So this is 50%, and then you can add it to the 34% in this side, which is between 0 and 1 standard deviations above the mean, and then we'll have that's equal to 100% of the people minus the 50% that's worse than the mean, and then minus the 34% that's between 0 and 1, and that'll give you 16% of the population. So if you pick a number in a random sample, there's a 16% chance, or it'll approach a 16% chance that you will get the number being one standard deviation above the mean. So, an abnormally high or low IQ person, is defined to have an IQ of 2 standard deviations lower or higher than the mean. So if the mean IQ is 100 and the standard deviation is 15, so what are the boundaries of the lowest? What's the boundary that defines a person with abnormally high or low IQ? It would be 100 minus 2 times 15, and this is an abnormally low IQ person. I'm trying to make this seem as less of a less offense. Give I can't speak English. To give less offense to the abnormally high or low IQ people as possible. I'm an abnormally high IQ person myself, so I don't mean to give offense to the high or low IQ people in society. So that's why I rephrased my words to not have any of those words that would be considered derogatory. So we have 100 minus 2 times 15 is 70, which is if you are less than 70, so 70 or less, you'll be considered as an abnormally low IQ person, and 130 or more, you'll be considered as a abnormally high IQ person. So what is the percent chance of having the abnormally high or low IQ? Well, we know that the percent chance of having the not an abnormally high or low IQ is in between right here, right? This is where you don't have an abnormally high or low IQ. So if you take 34 plus 13.5 plus 34 plus 13.5, you will have 68, and then so it'll be 34 plus 13.5 times 2, and then subtract that from 100. You will have 100 minus 95, which is 5%. So you have a 5% chance of having abnormally high or low IQ. This is not true, by the way. I've just made this question up. This is probably not true. So that's how you calculate probability for the bell curve. Now, though, what I'm gonna formally introduce you the idea of a z-score now. So a z-score is basically the exact number that you measure from the mean in standard deviations. So, for example, the z-score of 2, a z-score of minus 2, actually, a z-score of minus 2 would give you a z-score of minus 2 would give you 2 standard deviations below the rest, right? So, for example, if the mean is 500 and the z-score is 75, and not the z-score, the standard deviation is 75, what's the z-score of the data point in 360? We'll have 360 minus 500 divided by 75, which is this. 1.87 is the z-score. Minus 1.87 is the z-score. So, and there are several, we're going to be doing this question. There are several headlines of big money bank robberies, but generally the amount of money stolen is around $20,000, maybe $10,000 in some countries, or in the US, I heard actually. But let's say the standard deviation of this value is about 3,000. So more or less 3 people steal between 7 to 3, 7, about, yeah, 7 to 17 to 23,000. And most of the robberies are in between 14 to 26,000. So if a local bank robbery reports to have it stolen 43,500, what is the z-score of this robbery? Now, the distribution of this is probably not standard. Let's be honest. It's probably standard on a log scale, or on a log scale, but it's probably not standard when it comes to this, right? When it comes to the linear scale, and because there have been robberies of millions and billions, and that'll just shift the mean all the way up, and it'll be ridiculous, right? So this question isn't very good. Even though I made it, it isn't a very good question. But let's say it is, right? And so we're trying to calculate z-score. We're not trying to see if a question is good or not. That's for the next units. That's for 10.2, 10.3, 10.4. We can see if questions are good or not. So we have this 43,500, and then we can subtract it with the mean, which is 20,000. Right, so the general z-score formula is just z is equal to the unit, subtract the mean, and then over the standard deviation. So that will be over 3,000, which will give you around 23,500 over 3,000, which is around 7.83. So this is if the world really was like this, a $43,500 steal from a bank would be really, really, really rare. Honestly, it's still pretty rare to get 43,500 off a bank. However, it actually isn't that it isn't as rare as what the data says for it to be 7.83 standard deviations above the mean. That's about I'd say a 1 in 10 billion, probably more than a 1 in 10 billion chance of getting that. Which honestly, I don't even think there are 10 billion robberies in the entire history of the human race, right? Of the humanity. So that's why the question's pretty bad. So there's a way to find the probability at a specific z-score as well. So it's not just like at a specific range of z-score, or more than that z-score or lower than that z-score. So in this question 20 right here, we have a times the fire department takes to arrive at a scene of an emergency is normally 6 minutes at a standard deviation of 1 minute, right? So 6 minutes, standard deviation of 1 minute. So for about what percent of emergencies does the fire department arrive at the scene in 8 minutes or less, right? This is 8 minutes or less. So we could basically use the table. We're gonna use the table just for practice. So 8 minutes or less, it'll be 8 minus 6, 8 minus 6, and then divide by 1. So that's 2 over 1, so that's 2. So it's 2 standard deviations above. So the z-score is 2. Basically, the z-score is 2. So we can see 2 and then 0 right here. 2, 0, 0.9772. So this standard normal table is measuring the probability of the amount of times that it uh, they right. This is PZ is lower than A point B. So it measures the time that they do it in less than the time, right? They do it in less than the time that that the question asks. So it will be 8 minutes. It will be less than 8 minutes. So it's less than the data point, right? So if you want more than the data point, you have to do one minus. So it'd be 2, which is 97.72%. So 97.72%. Right. Next question is 5 minutes or less. That's the goal. So it'll be 5 minus 6 over 1, which is minus 1. Minus 1 is this. It's 1.1587, right? So this is 5 minutes or less. How many times does it go? How many times does the scene reach the emergency in 5 minutes or less? Well, it's right there. It's 15.87%. C. The fire department implements personnel changes that increase the standard deviation of the arrival times to 1.5 minutes. What are the advantages and disadvantages? The advantage is there are more kind of, well, actually there are less trips that are going to there are more trips that are going to take shorter in order to reach the place. But the disadvantage is there's also going to be a lot of trips that take longer as well, since the no, if if the goal of the fire department is to get everyone to the scene of an emergency in 5 minutes or less, then increasing the standard deviation would be a good idea. But if that's the only goal, and the goal isn't to if that's the only goal and the goal isn't to to not just go as quick as possible, then that would be a good idea. However, if the goal is to go as quick as possible, for the fire department to reach the scene of emergency as quick as possible, then the standard deviation has to be reduced, or the mean itself has to be reduced in order for it to be effective. So the next slide we have normal distribution. What is a normal distribution? I already discussed this. Basically, normal distribution is shaped like a bell curve, and there's a mean. The mean is equal to the median. So for example, is this a normal distribution? It's not. It's not a normal distribution. Not right, because whenever you draw the line, it doesn't look like a bell curve at all. It looks like a mountain kind of, right? It this isn't even a good curve. This isn't even like one of those warped curves that you normally get when you have a skewed right or skewed left graph. It's just kind of a disaster. However, this is pretty decent. This is a decent bell curve right here. So this is a bell curve, and this isn't. And notice that even though the whole graph moves to the right, like this, right here, this might be the distribution of test scores, right? When the whole graph moves to the right, it's still a good graph. It's still a bell curve because, well, we're not having the median not equal to the mean just by the whole graph moving to the right. It's just the median isn't right in the middle, right smack in the middle of the graph, right? But it's still equal to the mean. It's still it still separates the two parts quite equally, right? Whereas this, right, the median, you could see that this in this graph, the median is not equal to the mean, and in this graph, the median is definitely not equal to the mean, and a lot of students are worse, or a lot of students are better, right? So the normal distribution has to be norm. So in exercises 21 and 22, a normal distribution has a mean of 25 and standard of 2 to describe and correct the error in finding the probability that a random selected x values in the given interval. So we've already, so for 23 and 27, the mean is 25. So let's solve the question first. The mean is 25, and the standard deviation is 2. So if the value, I'm gonna use n, even though I'm probably not supposed to use n. If the value is in between the mean plus the standard deviation and the mean minus the standard deviation, then it's gonna be in between these two lobes. And if you remember from the other, okay, I'm gonna draw a bell curve out because this bell curve is inaccurate, and that's why it's wrong, because the bell curve is inaccurate. So we have this, and then we have the line going over, line going through it. So then we have, this is mean plus standard deviation, that's 27, and this is 23 right here. So we want to find the area of these first two lobes, and the area of these first two lobes, if you look at a few slides before, that would be equal to 34 and 34. So that's 34 plus 34, which is 68%, which is 0.68 and not 0.95. So this guy got it wrong because he thought the standard deviation was 1, not 2, and that's a pretty common mistake, right? Because just because the standard deviation is 2 doesn't mean you take two lobes of the graph and calculate their probabilities like that. So it's 0.68. And that's going to be it for z-squared standard deviations for the whole course, pretty much. Because we're not going to be talking about z-squared standard deviations anymore for the rest of the course. We're going to be talking about samples and populations. And that's a standard. That's a pretty useful standard for the SAT. So that's it. And see you next time for samples and populations.